Ladies and gentlemen, good day, and welcome to another session of Technical Sciences Grade 12 final and last push. And to be honest enough, we are currently running a nice series of revision lessons that are now assisting us to actually prepare for the paper that will be written on Friday. And yes, ladies and gentlemen, today we'll be looking into momentum and impulse. I intend on keeping the sessions less than an hour or even uh, less than 45 minutes. So what I'm going to do today is I decided to give a short, quick summary of the topic itself and immediately thereafter also emphasize key critical things and do one exam type of question to basically see what are the critical issues that one should be focusing on. Ladies and gentlemen, without wasting any time, let's get straight to it. I usually start everything somewhere in the circle and say this is now momentum and impulse. But now there are few things that one must be in a position of explaining, ladies and gentlemen, and this forms now what? Part of the definitions thereof. So the very first thing is, what is this momentum? It looks like it's an easy definition that we know by now, but what we need to emphasize there is just momentum is defined as a product of mass and velocity of the object. Velocity of the object. Why, Ntate Nambani, do you need to emphasize this? I need to emphasize that we are in a position of actually deriving a formula and an SI unit here. P, which will be the momentum, will be equals to mv, where m is just now the mass of an object in kg and velocity in meters per second. Then this means we are going to have this now as our SI unit. Why? Because such questions also, ladies and gentlemen, they will be assessed in a multiple choice type of a question. Now, if this is the case, what does it mean? It means momentum is actually a vector quantity. And the fact that it is a vector quantity, it means, ladies and gentlemen, we need to have both now magnitude and direction. So we cannot work or do problems related to momentum without actually doing what? Without basically having to choose the correct direction. An incorrect direction will influence the final answer thereof. And that is where we are losing majority of our marks. Ladies and gentlemen, let's talk about a collision as bullet number two. Why do we need a collision at bullet number two? It's very easy. A collision is an isolated event. Isolated event in which one or two objects exerts a force on each other. Each. Now let's explain this. You cannot have a collision or an object colliding on its own. it should actually be in a collision with a certain object, either a wall, another car, but at least we need to have two objects that are going to exert a force on each other. Let's highlight this. When they are in contact with one another, these two objects, Newton's third law, this is very, very important. Newton's third law is applicable. What do we mean by applicable? We mean that when we have two objects colliding, Newton's third law comes into play. When object A collides with object B, they both basically exert the same amount of force, but now in what? In an opposite direction. So these are issues that we need to understand when we have collisions in momentum, when we have a collision in terms of impulse, and believe you me, we expect something of this nature, a principle that we can use in order to explain the effects of a collision thereof. Now, how is this collision affecting the topic itself? It brings us to what we call at number 3, the change in momentum. The change in momentum. And we are going to use delta P for that. What is this change in momentum? It's basically easy thing to understand. We said change in momentum is equals to, or momentum is equals to P and V rather. So change in momentum basically means the change, which is P final minus P initial. But this is now V final minus V initial. What does this mean? It means for the change in momentum, the only thing that is changing, ladies and gentlemen, it is now what? The final velocity and the initial velocity of the object. So let's write it down to say the only velocity is changing in change in momentum. Because when you check, we still have now what? The very same object, which is only one object in this instance. But what will this mean? Or what will an issue of change in momentum occur? Ladies and gentlemen, once there's a change in the velocity of the object, we get the change in what? In momentum. And the only factor that is changing there, it is the velocity. So we are in a position of knowing the momentum of an object before and knowing the momentum of an object after. But if there's a change in velocity, is then we can only say, yes, ladies and gentlemen, we have change in momentum. But if there isn't any change in momentum, it means our momentum is going to be conserved. At the very same time, it goes going to be the same throughout. That Nambani, does it mean we can be in a position of drawing certain graphs that relates to momentum and impulse at the very same time a change in momentum? Yes, we can be in a position of doing so. Let's explain these few important graphs. The very first one, which is very easy to understand, will be velocity versus time. Very easy to understand. And its shape, ladies and gentlemen, it is something of this nature. Where now, plus minus, the plus minus only indicates direction, ladies and gentlemen. So remember, you must be in a position of choosing the correct direction. So if we say this is to the right, it basically means this will be to the left. If it is to the east, it basically says once it is below, it means we had somewhere here a change in direction, a change in direction. And this, ladies and gentlemen, the velocity versus time, because the velocity is changing, we can use this to actually understand the concept of change in momentum. I will come back again to this graph to explain now issues of impulse relating to velocity versus time. So velocity versus time is going to be one of the very much important graphs that each and every one of us must be able to interpret. Remember, the questions have been exhausted, so the examiner should try to bring some element of surprise. However, they will find us ready because we are trying to close now what? All the necessary gaps, ladies and gentlemen. Now, fine. If that is the case, what else can we add to our notes, which is very, very important? Let's start here at the epicenter again, momentum and impulse. Remember, the recording will be available so you can rewind as quick as you can, as how you please. The idea is to finish everything within the 45 minutes. Now, now, let's start with impulse. We spoke issues of momentum, changing momentum. Let's now quickly go to number 5. And number 5 is now impulse. Let's write it down. Definition, very, very important. And what does the definition say? The product, ladies and gentlemen, the product of the resultant force, acting on an object and the time the resultant force acts on an object. Definition 2 or 0, very, very important. The product, ladies and gentlemen, of time when it acts on an object. Can we have a quick formula? Yes, F net multiply by changing t is equals to changing p. Ladies and gentlemen, this side here, which is the product, this side represents the impulse. Now, this is the definition that you must give. No any other definition. Because the definition of saying impulse is equals to the change in momentum, we do not accept. I repeat, we do not accept the product of the resultant force acting on an object and the time the resultant force acts on an object. That is the only definition we are going to accept and we are going to mark. However, we'll see, but please note that this is now the definition that is acceptable. Now, even if you are going to use this equation, don't write impulse is equals to the change in momentum. You must write the formula, ladies and gentlemen, as it appears in the formula sheet. So it must read F net multiplied by changing t is equals to changing p. What is the SI unit? Very easy, ladies and gentlemen. The SI unit thereof will be something like Newton second. Very, very, very important. And now, we have the application of this impulse. We have the application of impulse in everyday life. Everyday life. Very, very important. First one, we can use this to explain the operations of airbags. We can use this to explain why the tennis player must move their hands back. Tennis players. We can also explain this in terms of crumple zones during accidents, D, as well as what we call the arrestor. Ladies and gentlemen, the principle here relates to the impulse. So we must be in a position of relating what is going to happen with an airbag. How is it assisting in our daily life? A tennis player, a crumble zone, a rester bed, a field worker, any other thing. When you get to the question of momentum and impulse, and you find that, but now this question is asking me to explain something of a daily life. Ladies and gentlemen, there are few bullets that you need to follow. And these bullets that you need to follow, believe me, they will assist you to get the 3 marks that the question will be. How does this thing assist? Ladies and gentlemen, first bullet is to say during the collision, the airbag or whichever one you are referring to, but this will be standard. Let's use an airbag. The airbag inflates. So the crumple zone will increase also the contact time. The tennis ball, the players of the tennis, by the time they move their hands back, they're actually increasing the contact time. And the same thing that the arrestor bets will do. So now what does that do? Inflates and the contact time of the passenger and the contact time of the passenger with the airbag with the airbag increases. Bullet number 2, then the longer the time, the longer the contact time, the lower the net force. Last bullet, according to, this is how you get your 3 marks. According to F net is equals to changing P over changing T. For the same change in momentum, for the same change in momentum. Why, ladies and gentlemen? Because our momentum did not change. The only thing that happened here was that the airbag, when it inflates, it actually increases the contact time. And when we have a longer contact time, or the contact time has increased, it means it has lowered the Fnet. According to what, ladies and gentlemen? According to Fnet is equals to changing P over changing T. That is the principle that we must use in order to explain all these applications of impulse in our daily lives. But we need to emphasize this is for the same change in momentum. So there isn't any change in momentum. Momentum here basically stays the same. Why? Because the only factor that is changing is now the issue of time. Let's move again, ladies and gentlemen. We are summarizing it nicely for us such that we know we have covered all the critical aspects. Let's move, and when we move, let's delete this line. Okay, fine. I think we can use this because we are just left with two things. Let's add another line here and another line there, and then we can use this side to explain this important concept. Also, we say it's momentum and impulse, but now we are looking into conservation of linear momentum. Let's take it up and we say that is now number 6, conservation of linear momentum. Stating the law very critical. The total linear momentum of an isolated system. The total linear momentum of an isolated system is conserved. Ladies and gentlemen, I prefer using this one. It's straightforward, easy to marks for majority of us. Now, when we get to the calculations, please start your everything with the sum of momentum initial is equals to the sum of momentum after. Please start there. Why? Because whatever comes after this, it is just an equation that is situation based. That equation will depend on what, ladies and gentlemen, on the information given. But now we want to see the application of the principle. So you must start there with the principle, and after the principle is then that you can be in a position of applying this. When and how can we apply this? Ladies and gentlemen, when we have explosions, two objects colliding and moving together after the collision, two objects colliding and moving separately, we have done and exhausted all possible questions here. What is important is please read the question in detail. Read the question very careful. There will always be something that is very tricky that the examiners are going to give us. So, but at least we know the application of conservation of linear momentum should be there, ladies and gentlemen. One critical aspect, it is at number 7. At number 7 is types of collisions. Types of collisions. Ladies and gentlemen, we have an elastic collision. We also have inelastic collision. But what is the difference now between the two? Momentum is conserved. Momentum is conserved. So now we cannot use momentum as a differentiating factor. So for us to differentiate whether a collision is elastic or inelastic, ladies and gentlemen, we must emphasize that the total kinetic energy before is equal to the total kinetic energy after. Total kinetic energy after. Or some people usually use the word total kinetic energy is conserved. Total kinetic energy is conserved. Now, this side, total kinetic energy is not conserved. Ladies and gentlemen, when you want to prove whether a collision is inelastic or elastic, you must have the sum of EK before half mv squared plus half mv squared. And you must also have EK after, which is just half mv squared plus half mv squared. You cannot conclude immediately to say they are equal. You cannot, or they are not equal. The first thing is we want to see you performing a calculation for the total kinetic energy before, total kinetic energy after, and immediately thereafter is then that you can compare the two. But what do we expect? A total kinetic energy is not conserved. So the sum of EK before is not equals to the sum of EK, the sum which is the total after. But what happened to this energy that is lost, ladies and gentlemen? That energy is lost, and it is lost in a form of heat or light, and at times sound, ladies and gentlemen. So we are trying to close all the gaps relating to momentum and impulse, ladies and gentlemen. So this is a nice quick summary for each and every one of us to have, because it basically emphasizes key critical concepts. So I have selected one exam type question that I wanted us to interrogate and look into. I believe it is a basic standard question, but it will assist us in terms of how we get to prepare fully for this particular examination. Ladies and gentlemen, and the question reads as follows. A truck of mass 4971 kg was traveling at 30 meters per second towards the east when it collided with a stationary car of mass 116, and after the collision the truck moved to the west with 18 meters per second. Now, ladies and gentlemen, key critical fee. Momentum is a vector quantity. It must have both magnitude and direction. So the fact that I'm being told of west, east, and things like that, it means I must commit and say I am choosing now, if this is my Cartesian plane here, and I have my west and then I have my east, I will say my east is positive, my west must be negative. Then I'm going to say, now I know what is going to happen and what will be the meaning of each direction or the value in terms of the negative and the positive. Now let's write there, ladies and gentlemen. We are told to say, calculate the momentum of the truck just before the collision. Very easy. P is equals to mv, ladies and gentlemen. The mass is 4971 multiplied by velocity, which is negative in this instance. Why? Because I chose to say anything and everything that is moving towards the west. Ladies and gentlemen, it must be negative. So I'm going to substitute my negative 30, and then I get the negative answer, which is 149130. But you get penalized for leaving a negative answer, because a negative answer needs to be interpreted in terms of the choice of direction. So we must now say, therefore, P is equals to, ladies and gentlemen, 149130 kg meters per second, but in which direction? Towards the west. That is where now my mark is sitting. So 1 mark for the formula, 1 mark for the substitution, 1 mark for the correct answer with the correct direction. So correct answer with the correct SI unit, as well as now what? The correct answer with the direction. That is only when, ladies and gentlemen, we can give you your full marks that you desire. So critical information, SI unit, and choice of direction, especially when we work with vector quantity. Ladies and gentlemen, let's quickly move. 312, determine the magnitude of the car's velocity after the collision. Very easy, because we know that the car was now stationary, but we have two objects that are now colliding. So we cannot use P is equals to mv. The only principle that allows us to accommodate two objects that are colliding is the conservation of linear momentum. So the sum of momentum before is equals to the sum of momentum after. But what happened before? We had the car plus we have the mass of the truck. What happened after? They moved separately, so I still have the car independently. I also have now the truck independently. Ladies and gentlemen, hence we say, please start with the conservation of linear momentum. Because why, ladies and gentlemen? This part of mcvc plus mtvt, it basically comes from the information that is given. So that will be the part that keeps on changing, but it changes because of different situations. Now let's substitute. We said our west is negative, so we will substitute, ladies and gentlemen, everything we have here. Let's start. Mass of the car 1116 multiply by 0. Let's change the color of this pen. Multiply by 0 plus the mass of the truck 4971, but it was moving west, so minus 30. And what do we have there, ladies and gentlemen? 1116 is the mass of the car, VC of the car, plus 4971, and we are told it is also moving to the west side, and then that must be now minus 80. So the choice of direction, ladies and gentlemen, very, very important. After very deep mathematics, your final answer must be 5345 meters per second. In which direction, ladies and gentlemen? It must go to west. Why is it going to west? Remember, it was stationary, so the truck is actually pushing the entire combination of the car and the truck into this particular direction. So the answer will be negative, but we must interpret that final answer for us to get the west. Ladies and gentlemen, for easy 1 mark, at now 313, name the principles used to answer 312. Very easy, 2 objects. The only principle that allows us to work with 2 objects is conservation of linear momentum. So we must write to say the principle of conservation of linear momentum. 1 mark. Now, yesterday when we're doing Newton's laws, we agreed to say these questions of greater than, smaller than, equals to, increases, decreases, or remains the same, we should actually start by giving an answer or the reason for that matter. If we fail to give a reason, then we cannot choose the correct answer. So in this instance, it means you must work in reverse. And the reason why we work in reverse is very, very easy. It's very, very easy. Is for us to actually get to the correct answer. Because these questions, ladies and gentlemen, they usually have the negative marking. Negative marking, we mean if you choose an incorrect answer at 314, we don't give a mark for 315. Only because you are giving a reason for an incorrect answer. So best way is to start having a reason that will assist you to move into the correct direction. Let's find. Without any calculation, determine how the final momentum of the car compares with the initial momentum. Will it be greater or smaller than? Ladies and gentlemen, the answer is sitting here. Before the momentum was 0, before the collision, the momentum was 0. It's 2 marks. Now what else happened after? After, because of we have a velocity of 53,545, which means this part here will now become greater or bigger. Why? Because, okay, the momentum increases with an increase in velocity. That is now your 2 marks. But what can we say now at 314? 314, very easy, ladies and gentlemen. The answer is going to be greater than. Why, ladies and gentlemen? Because before the collision, the momentum was 0. After the collision, the momentum increased with an increase in velocity. So the only correct answer there must be greater than. I repeat, you cannot just choose greater than without any reason. So please think deeper with your reason, and your reason will always be based on laws or principles for that matter. Please, let's apply either a law or a principle. They usually assist us in terms of giving the correct reason. So you cannot have a reason, ladies and gentlemen, without or a good answer without necessarily having a reason for that matter. So let's quickly go to 3.2. Let me just clear this thing here. Now we are at 3.2. At 3.2, the effective use of seat belts was demonstrated during a car crash test at the motor manufacturing plant, and the car hit the wall with a momentum of 24,300 kg meters per second and took 1.2 seconds to come to rest. V final is equals to 0, and we have now our momentum before, which is equals to 24,300, and we are given there our contact time, and they say at 321 use the physics principles to explain how seatbelts can serve as a protection during the collision. Ladies and gentlemen, let me not waste your time. What I'm going to do, I'm going to highlight this. After highlighting this, I'm going to copy and just paste everything here. Why? Because, ladies and gentlemen, believe you me, this is exactly the same principle throughout. %. Now, during the collision, the airbag inflates and the contact time of the passenger with the airbag increases. The longer the contact time, the lower the F net. According to the equation, changing P over changing T for the same change in momentum. Ladies and gentlemen, hence I said this is standard. This is the only way or the only best way of actually answering this question. 322, calculate the impulse experienced by the car. We said impulse is F net multiplied by changing T is equals to change in momentum. But now what is this change in momentum? Is momentum final minus momentum initial. But now, ladies and gentlemen, what is our final momentum? Our final momentum is equals to 0 because we are told that it is coming to rest. Minus now what, ladies and gentlemen? Minus the 24300. It's giving us negative 233. When then our final answer there, it basically says 2433 Newton second. Newton second, ladies and gentlemen. And that's how easy it gets in terms of understanding how to answer this question. But because the answer was negative, we can say away from the wall. Away from the wall. Let's quickly duplicate. And then they say now the wall was built to withstand a force of 80,000 newtons. Now, by means of calculations, if this wall will be able to withstand this test, the formula is still the same, ladies and gentlemen. We know that we have our answer here, which is negative 24300. F net is what we want. Multiply by 1,2. F net, ladies and gentlemen, is equals to something like 20500 or 250 newtons. And this, ladies and gentlemen, it is less than 80. So yes, the wall will withstand the impact. And yes, ladies and gentlemen, that is how now you best approach momentum and impulse. And I just hope we tried to explain all the critical issues related to this topic, because ladies and gentlemen, this is a nice, somehow complex and easy topic at the same time. Ladies and gentlemen, without wasting any time, may the great Lord give you strength and bless you endlessly, achieve everything that you desire, give you strength to actually do well in these final examinations. Without wasting any time, thank you very much and have a lovely day.